Hello everyone from Math 1340, Statistics. It's Professor Winston here again with a video on your KnewtonAlta homework, section 3.5, titled Tree and Venn Diagrams. Now you've already seen examples of Venn diagrams before, but you'll see them again here and be introduced to tree diagrams as well. And these are tools, diagrams that are useful in helping you determining probability and also counting. Alright, so I'm just going to jump right into it. Now there are only two objectives in this homework, so again it should be relatively short. One of them is use a tree diagram, the other one's about Venn diagrams. Alright, so use a tree diagram to list outcomes and compute probabilities. Alright, so this is what a tree diagram looks like, by the way. But just as I've been saying every video, if you come across an objective for the first time and you feel like you need some more help with that objective, or you're unfamiliar with the material, I would click on More Instruction every time I come across a new objective. Alright, so let's see what they have to say about tree diagrams. So sometimes when probability problems are complex, it can be helpful to graph, or draw a picture of the situation. A tree diagram is one tool that can be used to visualize and solve conditional probabilities. A tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. So they'll go over this first example here. Right. So an ice cream parlor claims to have more than 14 possible sundaes, and their slogan is, "Try a new one every day for 2 weeks." Two brothers visit the shop to test out this claim. They are presented with the following menu. So you get either 1 or 2 scoops. You can have they have vanilla ice cream, chocolate ice cream, strawberry ice cream, and they have rainbow sprinkles and fudge sauce as toppings. For each sundae, a customer is allowed to choose the number of scoops, 1 or 2, one flavor of ice cream, which is only 1, okay, and 1 topping. Okay, so a pretty weak sundae, but still, 1 of each. All right. So now I'll actually write out I'll draw the tree diagram here on a piece of paper. All right, I'm going to scroll this down and pull up some paper here. Now I know they got the diagram there, but I want to show you how it was drawn. Right. So you kind of go through in each line of the diagram. Right, so this is a tree diagram for making these sundaes. Right. And for each line, each level of the tree, we have our different choices, right? The different parts of the experiment. The experiment here is putting together a sundae. So you see the first choice is, how many scoops. Right, the number of scoops. And on that level, I list them. I can choose either 1 scoop or 2 scoops, and that's it. Right? So on that level, I put those 2 choices, and then I start branching off. All right. The next choice being made is the type of ice cream. So on the next level of the tree, I have my choices of ice cream. Now here's where these branches come into play. For each part of the level above, I branch off with the number of choices I have for the level below, meaning this. So if I chose 1 scoop of ice cream, right, and then I went to choose what kind of ice cream, I have 3 choices, right? The vanilla, the chocolate, and the strawberry. So off of this, the word 1 got 3 branches, where you have vanilla, chocolate, and I'll just put CHOC for chocolate, or strawberry. And on this level with the ice cream. But also, what if I had chosen 2 scoops? And then again, every new choice takes you down new paths of the tree. If I chose 2 scoops, then what choices would I have? I would still have the same 3 choices, right? Because you're asked to first select how many scoops, and then select what kind of ice cream do you want those scoops to be, and you can only select one kind. So again, if I chose 2 scoops, I'd have the choices of vanilla, chocolate, or strawberry. Okay, so you see, so right now there are 6 possibilities. 1 scoop of vanilla, 1 scoop of chocolate, 1 scoop of strawberry, or 2 scoops of vanilla, 2 scoops of chocolate, 2 scoops of strawberry. Right? So right now there are 6 possibilities, but I'm not done. Right? I'm not done making the sundae. So then the next level down is my next choice, the next step in the experiment, and that's choosing the toppings. So in each of these 6 spots of the previous level, I'm going to have branches coming off. And I'll have a branch for each choice of topping I have. So if I chose 1 scoop of vanilla, and then I say, hey, choose a topping now, you have 2 choices. So there'll be 2 branches coming off this vanilla here. And same thing for the chocolate. There'll be 2 choices there, right? Because there are 2 choices of topping, and same thing for the strawberry. And then over here, same deal. If I had 2 scoops of vanilla, or 2 scoops of chocolate, or 2 scoops of strawberry, there'd still be 2 choices of topping. So again, each of these previous ice cream level entries get 2 branches. Right. And I get toppings of, now remember, there were the sprinkles or fudge. All right, I'll just put sprink for sprinkles or fudge. And sprinkles, again, sprink or fudge. Choice of sprinkles or fudge. Choice of sprinkles or fudge. Sprinkles or fudge. Sprinkles or fudge. I just went S and F on the last one. Okay, sprinkles or fudge. And so now that's it. And that's it. That's the last level of the tree. Okay, this is a tree diagram for making a sundae, where I choose one of these. All right, so say I made I wanted 2 scoops of ice cream, and then I choose my ice cream, 2 scoops of vanilla, and then I choose the topping. I want fudge, and count the numbers at the bottom. All right, at the very end of the tree diagram, or at the very bottom, count how many sundaes can I make, is how many finishing branches there are. And there are 2, 4, 6, 8, 10. There are 12 total sundaes that could be made. All right? And you could list them off by just following the branches, following the paths. 1 scoop of vanilla with sprinkles. 1 scoop of vanilla with fudge. 1 scoop of chocolate with sprinkles, 1 scoop of chocolate with fudge, 1 scoop of strawberry with sprinkles, 1 scoop of strawberry with fudge, 2 scoops of vanilla with sprinkles, 2 scoops of vanilla with fudge, 2 scoops of chocolate with sprinkles, 2 scoops of chocolate with fudge, 2 scoops of strawberry with sprinkles, 2 scoops of strawberry with fudge. Those are the 12 different kinds of sundaes you could make if you had to choose a sundae the way they're saying. Right. Okay. So yeah, very. Now you see that there I made a tree diagram. There, there are 12 outcomes, right? 12 possible sundaes. So the slogan is false. Right? They said you can make 14. But obviously, I wouldn't want to do this when there are much, much larger numbers. This wasn't so bad when there are like just 2 choices and 3 choices and 2 at each level. Like, hopefully you see that it would be kind of a pain to make a tree diagram when numbers are large, right? Numbers of choices are large. But let's see if the examples look like later. All right, and then this is just probability again. Remember, the probability of an event is the number of times that event can occur divided by the total number of outcomes in the sample space. Right, we've seen this before. All right, and then another example, they draw another tree. All right, so take that same tree, I guess. Right, looks like the same tree that I just made here, right, on my paper, with the different Sundays that can be made. Now the question is, the brothers in the first example decide to try the lucky Sunday, where the employees of the ice cream parlor choose the sundae for them. The question is, what is the probability that the brothers will end up with a 2-scoop chocolate ice cream fudge sauce sundae? Well, if you look at that, a 2-scoop chocolate ice cream fudge, I'm following the paths down the tree. 2-scoop chocolate ice cream fudge sauce sundae. That's just one path out of the 12, right? Remember I said it ended with 12. So the probability of getting that particular sundae is 1 out of 12. Simple as that. B, what is the probability that they will have a sundae with strawberry ice cream? So I count all the paths that have strawberry in the path. So there's, 1 scoop strawberry rainbow, 1 scoop strawberry fudge. That's 2 paths off of that strawberry. 2 paths with strawberry over here. And there are also 2 paths with strawberry over here. So there are 4 outcomes out of the 12. There are 4 paths down this tree out of the 12 where I'm having strawberry ice cream. So 4 out of the 12, that's 1/3. All right, see, 4 out of the 12, 1/3. So yeah, so it's a nice picture, to help you find probabilities, to help you count outcomes. Again, I wouldn't really make a tree diagram if the numbers were too large, but it is a nice way to visualize a situation. All right, so I'm going to leave this one. I'm not going to do this one. We'll get to a problem. Now notice, this is important. All right, this is important here. The fundamental counting principle. So suppose a first process has A possible outcomes, and a second process has B possible outcomes. Then the total number of different outcomes is going to be A times B. This extends to any number of outcomes, right? Adding a third process with C possible outcomes brings the total to A times B times C, and then if there was a fourth process, A times B times C times D, etc. All right, so look back at that tree diagram I made, right here. See, there were 3 processes. Remember, and there were 2 choices of scoops of ice cream. There were 3 choices of the flavor, right? Vanilla. There were 2 choices. You could get 1 or 2. There were 3 choices of the flavor, vanilla, chocolate, strawberry. And then there were 2 choices of topping, sprinkles or fudge. And remember at the end I said there were 12 total sundaes, right? Because again, I'm doing these processes back to back to back like this. And then if you do that, if you apply the fundamental counting principle, you can say without making a tree diagram how many sundaes can be made if you only choose one of each, right? If you can choose more of each, then there's going to be another. We'll talk about counting that way later. But if you're only choosing one of each, one of these numbers of scoops, one of these flavors of ice cream, one of these toppings, then the total number of sundaes is going to be 2 times 3 times 2, right? The numbers of scoops to choose from times the number of flavors to choose from times the number of toppings to choose from. And 2 times 3 is 6, times 2 is 12. Right? And I said that earlier. And you can see that in the tree diagram. There were 12 total sundaes. So that's an example of an application of the fundamental counting principle. All right. So if you have so many processes back to back to back where you get 1 choice each, the total number of possible outcomes is the product of those numbers of choices. All right. So they give another example here. Now this is one where I definitely would not do a tree diagram. Now they might draw one. No, they don't. Okay. Yeah, because there'd be four, I'm making four choices. See, they're making a pizza, and to make a pizza, each customer must select one. Again, it's only when you have making one selection each. And we'll like I said, we'll talk about what if I have to select more, or what if I could select none. But if you have to select one from each category, so I pick a size for the pizza. There are three choices of size. Then I choose a sauce, garlic or marinara. Then I choose a cheese, and there are three choices of cheese. And then I choose a topping, one topping out of these six. So that if you were only allowed to select, if you had to select just one of each, size, sauce, cheese, and toppings, how many total pizzas are possible? Well, according to this fundamental principle, and again, you could make a tree diagram. It would just be really huge. You'd have 3 times 2, which is 6, times 3, which is 18, times 6, which is 108. There'd be 108 different pizzas, and they do that here, that you could make if you chose one of these, one of these, one of these, and one of these only. All right. And then what is the probability that a randomly selected pizza by the group of friends will have pepperoni on it? So again, you think about your choices. You'd have 3 choices of size, so 3 times 2 choices of sauce, 3 times 2. 3 choices of cheese, so 3 times 2 times 3, that's 18. And they said it has to have pepperoni. So you have one choice. So 3 times 2 times 3 times 1. That'd be 18. 18 out of 108, which is 1/6. Right. And it just said you could also have just said that, noticing that pepperoni is 1 out of the 6 available toppings, you have a 1 in 6 chance of getting a pizza with pepperoni. All right, so you've seen tree diagram and the fundamental counting principle, and again, how to calculate probability. All right, so let's get into a problem. All right, so here we're given a tree diagram. All right. So in a game show, so I'm not going to draw this one out. You can see the paths, hopefully, in blue and green and red and all this. So in a game show, contestants are given the opportunity to win a new car if they correctly choose the winning door 3 times in a row. So that's how you win. You have to choose the winning door 3 times in a row to win the car. So in the first round, they must choose between 3 doors, one of which is labeled win, so then the other 2 are lose. So you see in door number 1, see there's one labeled win, the other 2 are labeled, not win or lose, right? Then the next choice is, after you choose the first door, you choose a second door, a second process. But you only choose from 2 doors, which one of them is win and the other one's lose. So you see how each of these door 1 labels has 2 branches coming off of it with win, lose, win, lose, win, lose. So far 6 possibilities. And then there's a third door. In the second round, their options are shown below. All right, and then I guess there's a third door with the same thing. Right? In the second round and third round. So you see the third round, they pick between 2 doors. So again, each of these from door number 2, each of these has 2 choices off of it, and there's a win or a lose door. So what's 3 times 2 times 2? That's 12. Right? That's 12, and you can see the 12 paths. Right? There are 12 ending spots on the bottom of the tree. So the question is, they are blindfolded and are not given an opportunity to see the doors beforehand. What is the probability that a contestant will not win a new car? All right, so I'll keep the tree up there and pull up some paper. Again, hopefully this is big enough for you to see. All right, so you can see the tree. Now remember, they told us in the problem here that winning a car, to win the car, you have to select win, win, win. You have to do that path. Right? You had to select 3 winning doors in a row. So what's the probability of winning the car? So I select how many ways can we win the car. Now looking back, hopefully you can see my cursor moving around on the tree here. How many of these paths, right, these 12 paths from door 1 to door 3 have win, then win, then win? Well, not these ones that start with lose, obviously. So I start here, win, then there's the win there, and then there's the win. There's only one path, win, win, win. So the numerator here is only 1. There's only one way to win the car, only one path to winning. And how many total paths are there? I already said it. It's 3 times 2 times 2. And you can see at the bottom there are 12 total paths. All right, so the probability of actually winning the car is 1/12. Now what about the probability of, now they're asking here, what's the probability that the contestant will not win the car? So hopefully you remember that this is called the complement of that event, right? There's winning the car and then not winning the car. Now hopefully you recall this rule from earlier in the chapter. Remember the probability of an event, say A, plus the probability of not that event, which is A bar or A prime. Remember it was either A bar or A prime. It was not A, the complement of A, is always going to be equal to 1 or 100% if you have percentages. So if the probability of winning the car is 1/12, the probability of not winning the car is 11/12. Right? They would add up to 1. And you could also do the relative frequency thing where you count how many ways can you not win the car. Well, of these 12 paths, 11 of these paths, except for the win-win-win, all of the other 11 you fail to win the car. So this probability is 11/12. So I'll highlight that dot there with the 11/12, submit my answer, and looks good. All right. Let me show you this stuff here. All right. Okay, so here, this one. A company is planning its spring advertising campaign. Its marketing team is planning to mail out different types of advertisements at random to their town's residents each week. They have the following types of advertisements ready. So in week 1, they send out either a small poster or a brochure. In week 2, they send out a leaflet, a postcard, or a brochure. And in week 3, they send out a business card, a postcard, or a small poster. How many different possible ways can a resident receive an advertisement? So I could make a tree, all right, and I'll show you. Right? I'll pull up a piece of paper here. You can make a tree where the processes here are the weeks. Each week, a resident's getting a different kind of advertisement, right? And they're only going to get one kind. So if you think, here's week 1. They can get a poster. I'll use P for poster. All right, P for poster, and brochure. All right. So in week 1, they're either getting a poster or a brochure, but not both. Right. This fundamental counting principle is only if you get one thing at each level. Week 2. Again, everything from week 1 is going to get branches, right? And in week 2, you're getting either a leaflet, a postcard, or a brochure. And actually, I should probably, for small poster, I'll put SP for small poster. SP for small poster, because I want to put P for postcard. Right. Okay, so then the next week, they're giving out 3 things. So each of these up here will have 3 branches. All right, each of these up here will have 3 branches. They're giving out 1 of 3 things. So in week 2, you can either receive a leaflet. I'll use L for leaflet. A postcard, so just P for postcard. Again, SP is for small poster. And a brochure, or a brochure. All right. And again, B represents brochure. So L, leaflet, postcard, brochure. All right, so far 6 possible outcomes from after week 2. Right, and that was 2 times 3, right? The fundamental counting principle. Just keep multiplying. Then in the third week, they're giving out, again, one of 3 things: a business card, a postcard, or a small poster. So each of these outcomes from week 2 is going to get 3 branches, because again, you have 3 choices every single time. So 3 branches off of each of these. And then every single one of these branches, in week 3 they're giving away a business card. I'll put BC for business card, or a postcard, P for postcard, or a small poster, SP. So BC, P, SP, business card, poster, postcard, small poster, business card, postcard, small poster, business card, postcard, small poster, business card, postcard, small poster. And look, there are 3, 6, 9, 12, 15, 18 possibilities. 18 possibilities, 18 different outcomes. Now I know you didn't have to, and you don't have to do the tree diagram like I just did. Remember, you just there were 2 choices from week 1, times there were 3 choices of advertisement from week 2, times there were 3 choices of advertisement from week 3. 2 times 3 times 3, 18. 18 possible outcomes. Okay, so that's all that's being asked for here. So again, you didn't need to make the tree. Please, don't waste your time making the tree. Now, if they ask for a probability deal, maybe the tree will come in handy. So I go through there, and then I believe, okay. All right, so now another question related to the same objective, all right, tree diagrams. So here, a credit card company requires that its customers choose a 3-digit numerical code to access their online account. Each digit should be chosen from 0 to 9, right? So there are 10 choices for each digit. So how many different 3-digit codes are there? Yeah, I'm pulling up some paper, and this is using the fundamental counting principle. All right, if you think about it, now it would be silly to make a tree diagram for this, because watch, if I made a tree diagram, right, you choose your first, there are 3 digits you're choosing. So I choose the first digit, so I can choose from 0 or 1 or 2 or 3 or 4 or 5, and already you're seeing that this would be an annoying tree to make. And then I would choose from then I choose the second digit in my passcode, and you'd have 10 branches, and with 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and you'd have 10 of those branches off of every single one of these. I mean, it would be kind of ridiculous, right? It would be I'd need a lot more space if I was going to make a tree. What I like to do is just think first digit times, because again, I'm choosing them in succession, one right after another. They're not happening at the same time. They're one process, another process, another process, right? Back to back to back. So the first digit, my choice for the second digit, my choice for the third digit, and I just count. This is that fundamental principle of counting. I have 10 choices for the first digit, right? 0 through 9, times 10 choices again for the second digit, right? They can be the same number, times, and then another 10 for the third digit. So this is 10 to the third power, or 1,000, right? There are 1,000 3-digit codes possible from 000 up to 999. All right, so I'm just entering 1,000. Again, that's that fundamental principle of counting. So another one here. Now this one they give us, again, they give us a tree diagram because it's not that, there aren't that many choices each time. And the total number of, the real estate manager of a commercial building needs to fill 3 empty spaces. The options for each store are the following. For store 1, so basically he's gonna make, this real estate manager is gonna make store 1 a grocery store. And then the manager decides, for store 2, they're going to make it either a pet store or a restaurant or a gym, right? One of these things. And then for store 3, they're going to make it a hardware store or a pizza shop. So for all 3 together, right, store 1, store 2, and store 3, there's 1 times 3 times 2. There's 6 possible outcomes, right? And you see the 6. There are, see how the bottom of the tree here has 6 ends to it. There are 6 paths. So what is the probability that the group of stores will have a restaurant or a hardware store or both? Right. So remember, this is the probability of A or B. Right? The probability of having a restaurant or a hardware store or both. So again, I count the number of paths that have a restaurant or a hardware store or both in the path. So one of them is grocery store, pet store, hardware store. That's one path. Then the other path doesn't have either, right? Grocery store, pet store, pizza shop. That doesn't have either restaurant or hardware store. So far I got one path going this way with a hardware store. Then you got the grocery store, restaurant, hardware store. That's 2 paths with either a restaurant or a hardware store. Grocery store, restaurant, pizza shop. That's 3 paths with either a restaurant or a hardware store. And then grocery store, gym, hardware store. So four out of these 6 paths have either a restaurant or a hardware store or both. So you can put 4 out of 6, which reduces to 2 out of 3. So you have like a 66, 67% chance, 2/3 chance of selecting a path with either a restaurant or a hardware store in it or both. Hopefully that made sense, right? Just counting these paths if you're given a tree diagram. All right, now the other objective is on these Venn diagrams. Now you have seen Venn diagrams before, all right, in previous sections, where circles or ovals represent events. And in this particular section, they'll typically be telling you how many objects are in that event. How many objects, how many people are in the circle. In a certain region. All right, so again, a new objective here. I'm going to click on More Instruction and read through the Venn diagram thing with you. So sometimes when the probability problems are complex, it can be helpful to graph the situation, as they said with a tree diagram. A Venn diagram is a tool that can be used to visualize and solve conditional probabilities, or just any probability really. A Venn diagram is a picture that represents the outcomes of an experiment. It generally consists of a box that represents the sample space, S, or the universal set, right, the set of all possible outcomes, together with circles or ovals. The circles or ovals represent, events, sets of outcomes. So look at this first example. Right? So suppose an experiment has the outcomes 1 through 12, where each outcome has an equal chance of occurring. Say event A has the outcomes 1 through 6. So you see down here, the big box represents everything. The numbers 1 through 12 will be all inside the big box, S for the sample space. This oval with A above it is got the outcomes 1 through 6. B is the event with outcomes 6 through 9, as you're seeing here with this oval. And they both have the 6 in common. So you see how that's in the overlapping region for those 2 ovals. See A and B, that's the overlapping region, is just 6. A or B, remember, was all the outcomes in A or B or both. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then you see on outside that, see the 10, 11, and 12, right? Those weren't in A or B, so they're outside, but they're still in the sample space. Right. Now, often, what we're more interested in are the frequency of each event. How many elements, how many outcomes are in each event. So you could redraw this diagram up here, say, hey, again, the big box represents the entire sample space, and the total of all the numbers should be 12, right? The outcomes are 1 through 12. And you see 5 plus 1 plus 3 plus 3, that's 12, right? There should be 12 outcomes total in the big box. You have a circle for event A, a circle for event B. See, there was only one outcome in their overlap, so you see the number 1 there. There were 3 outcomes that were in B but not in A, so the number 3 there. There were 5 outcomes that were in A but not in B, so you see the 5 in this region. And then there were 3 outcomes on the outside that were in neither A nor B. So you can put numbers or percentages. You might see, I'll just kind of roll through. You might also see Venn diagrams where they'll tell you the relative frequency of every space. What percentage of the outcomes are in this region, in this region, in this region. And the total of all the percentages should be 100. Right? You see 30 plus 20 plus 5 plus 45 here. The total of all your percentages for all the regions should be 100%. All right, so let's get to a problem here. I don't think these are too terribly difficult. All right, so here we're given a Venn diagram. All right, and it says a survey of students in a class reports who plays video games and who plays board games. All right, the following Venn diagram displays the results. So let's see how to read this, right? You got, so the big box represents the entire class. And if you add up all the numbers here, 15 plus 9 is 24, plus 19 would be 43, and then plus 7 would be 50. So there are 50 students in this class. See, 9 of them are in the overlapping region between the video game circle and the board game circle. So 9 students said they play both. 15 students said they just play video games, not board games. And 19 of them said they just play board games, not video games. And 7 of the students said they don't play either. They don't play board games or video games. All right, so using these numbers, we're going to say, given that a random student does not play board games. So again, notice the word given that, right? Remember conditional probability. Given that a random student does not play board games, what is the probability that the person also does not play video games? All right. So I'll pull up again a piece of paper. All right. I'm going to have a V represent play video games. All right, so V will represent plays video games. And I'll have B represent plays board games. All right. So the question is, let me get rid of the paper here again. It says, all right, given that a random student does not play board games, what is the probability that the person also does not play video games? Okay, so I'll actually pull that up on a bigger sheet, fill the screen up with a drawing of the Venn diagram as well. Okay, so I've drawn it up here. Same diagram. We're asked to find, they said given, right? Remember, given that, now this is B prime or B bar, this is not B. They said given that a student does not play board games, find the probability that that person also does not play video games. So that's again V prime or not V. You can put a bar over that. Just not V, not B. So if we're given this, that means our denominator, right, the students we're looking at, we're not looking at all the students. We're given that the student doesn't play board games. So we're looking at only the students outside the circle for B, the circle for board games. So you see the students that do play board games, there are 28 of those, 19 and 9. there are 28 students that play board games. So the outside of that, 15 and 7, there are 22 students that don't play board games. So again, that's what's given. So I'm only looking at these people. I'm only looking at the given people. And then it said, of those people, how many of them don't play video games? So of these 22 people, right, outside the board games that don't play board games, how many of them don't play video games? The 7, right, because these 15 do. The 7 don't. So it's 7 out of 22. Okay. Now you could have also done this, right? Remember our conditional probability. You could have also used this formula, right? The probability of, I'll do the bar this time, not V given not B. What's the probability, given that the student doesn't play board games? What's the probability that they don't play video games? Remember there was also this formula, the probability of not V and not B divided by the probability of the given event, the probability of not B. All right, so this time, for these probabilities here, these aren't conditional. So the denominator is going to be out of 50. These are both fractions. They'll both be out of 50. Right? The whole class has 50 students in it. Right? I counted up the numbers earlier. So out of those 50, how many don't play video games and don't play board games? So that's the 7. Right? Those 7 people. So 7 out of the 50 play neither. Divided by, and then what's the probability that you pick a student out of these 50 and they don't play board games? So out of these 50, how many of them don't? Again, just here's the board game people, these 28. So the ones that don't play board games are the 22, the 15 and the 7. And then, you can see hopefully that the 50s would eventually cancel and I'd be left with 7 out of 22. So however you want to see it. All right, you get 7 out of 22. So back here. And then it says provide your answer below. It says give your answer as a percent rounded to 2 decimal places. Alright, so I'll pull the calculator up and we'll do, I said it was 7 out of 22, right? So 7 out of 22. And then as a percent, I go times 100. I did times 10. So times another 10. I mean, you could probably see it from the beginning. So it's 31.8181. So if I round that to 2 decimal places, that would be 0.82, right? Because you got 8 after that, you bump it up. So this is the probability of a person, given that the person doesn't play board games, the probability that they don't also play video games is approximately 31.82%. All right, so I'll enter that. Submit. Wonderful. All right, see, they get the 7 out of 22, as I said before. All right. There's another one. Now this one you have to fill in the blanks for the Venn diagram. And you see there's also one outside the circles. Pay attention. So here, a university surveys 50 students, 50 undergraduates, to learn more about students' class preferences. They find that 25 of the students like to take online classes, and 35 of the students are freshmen. So say event A is the students that like to take online classes, and event B are first-year students, the freshmen. And we're given the following conditional probabilities. So this is the probability of liking online classes given that you're a freshman is 15 out of 35. Whereas the probability of being a freshman given that you like online classes is 15 out of 25. All right. Fill in the Venn diagram with the number of students for events A, B, A, and B, and not A or B, right? The outside one. All right, so whatever happens, these numbers that I enter, all 4 of them need to add up to 50. All right. And they said 25 of the students like taking classes online. So in circle A, the two numbers in circle A need to add up to 25, and it said 35 students were freshmen. So in circle B, these two numbers need to add up to 35. Now, this first probability they gave me, see the A given B. So remember the denominator here tells me circle B has 35 students in it, but 15 of those are also in A. That tells me the middle here is 15. 15 of them, 15 of the 35 students, that means there'd have to be 20 here, to make a total of 35 students in circle B, and 15 out of those 35 are also in A. And then this conditional probability, the probability of B given A, remember that means you have the numerator is how many students are in circle B that are also in circle A. Right, and so circle A should have 25 students. You got 15 here. That means you need 10 here. Right, so in circle A, 15 out of the 25 are in circle B as well. Right, conditional probability. Then these numbers, right, add up to 45. Right, 20, 10, and 15 add up to 45. So that means out here are the other 5 students. Right, again, all four of these numbers need to add up to 50. So again, hopefully not so bad. And they explain all that here. All right, so this is another probability deal. All right, here we're given a picture. It says a group of high school students reports who has a job and who plays sports. The information is presented in the following Venn diagram. So 20 of these students have a job but don't play sports. 8 have both, do both. 16 play sports but don't have a job, and 24 do neither. Add these up. There's 28 plus 40. There's 68 students. There are 68 students represented by this Venn diagram. All right. So get again another conditional. Given that a random student has a job. So you're talking about the students only in the blue circle. So the 28 students. So I'm going to be dividing by 28, not 68, because we're given that the student has a job. So I'm in this blue circle only. What is the probability that the student does not play sports? So of these 28 students that have a job, you see that 20 of them don't play sports. So that's 20 out of 28, which reduces 20 out of 28 reduces to 5/7, right? 10/14, 5/7. So if I enter as a fraction, right, final answer is a fraction. I don't know. It might take 20 out of 28, but I reduced it to 5/7. Okay. And again, you saw me do a problem like that already earlier on paper. All right. And here we're given another similar one. All right. Class of 8th graders reports who plays music, who plays sports. It's the same kind of thing, except music instead of a job. Another given, right? Given that a student does not play music. So how many students do not play music? 16. See, all the students in the blue circle, right? These 23 students, they do play music. We're given that the student that we're looking at does not play music. So only these 16 people. Of those 16, how many do not play sports? What's the probability that they do not play sports? So of these 16 who do not play sports, 6 of them. So 6 out of the 16. 6 out of 16, right, which would reduce to 3/8. 3 out of 8. Again, you've seen me do one like that on paper already, so I'm not going to write that one down. And that seems to be it. Right? So again, Venn diagrams I feel are the easier part. I mean, the tree diagrams and the fundamental counting principle, that's not too terrible either, if you think about it. All right, so hopefully this video is a good enough guide for you to work through the section 3.5 homework on your own. Again, you're not going to see the same order of questions, the same numbers that I did exactly, but the objectives are the same, the way you would do the problems are the same, the kinds of problems you're going to get are the same. So again, hopefully this video is a good enough guide for you on your own assignment working. And let me know if you have any questions, of course, and thank you very much for watching.